In the previous class, we started this example where we said that the two variables are hydrocarbon level, yes, and purity, y. Okay. The first part asked us to draw a scatter plot. Of course, in exam, we will not ask you to draw the scatter plot, but we will give you the scatter plot and ask you to interpret the scatter plot. So the first question says draw a scatter plot and comment on the nature of the relationship. We drew the scatter plot and we said that it's a linear, positive, strong association between X and Y. We confirmed that observation by finding the correlation. It was 0.93 with a positive sign, which confirms that the relationship is positive, linear, and strong. We found the fitted regression line, which was 74.28 plus 14.9 times X. We estimated the standard error of the standard deviation of error using the square root of MSE, which is 1.0867. We found the standard errors of B0 and standard errors of B1, and we were here. Close the store. Close this door. Now, for this question, the question clearly doesn't mention what was required. It was in terms of a statement. And from the statement, you are supposed to recognize that you are supposed to draw the confidence interval for what? So you need to read the yellow highlighted part and see what is the yellow highlighted part. What is the yellow highlighted part? Yellow highlighted part is the average change in Y due to a unit change in X, which is slope. Average change in Y due to a unit change in X, which is slope. This thing is actually beta 1. So what is the question asking you to do? Construct a 95% confidence interval for beta 1. Now you will go to the formula sheet and you will find this. A 95% confidence interval for beta 1 is beta 1 hat plus minus T alpha by 2 with n minus 2 degrees of freedom multiplied by something here. The something is actually the standard error. Remember, this is the standard error. I will write the formula, but remember, this is the standard error. Sometimes they give you the standard error directly. So the formula is MSE over SXX. Again, remember, this whole thing is standard error of beta 1 hat. Sometimes in questions, they give you the standard error directly. You don't need to compute MSE and SXX, all that. So I will not go back to chapter 9 and tell you how to compute the critical value. I will assume you know it. For alpha equals 0.05, again, you will divide alpha by 2, look for the degree of freedom. This T value comes out to be 2.101. So you will plug everything inside the formula. Beta 1 hat you computed in part 3. Beta 1 hat was 14.9 something. 14.947. Plus minus 2.101 times standard error of beta hat. You don't need to plug everything in the formula now. Although you have MSE, you have SXX. But in previous part, you found the standard error of beta 1 hat using that formula MSE over SXX square root, and you found it to be 1.3169. So now use it. 1.3169. And this comes out to be 12.1802 and 17.7138. What will I say about this confidence interval in terms of interpretation? I will say that we are 95% confident that the average change in purity due to 1% increase in hydrocarbon level is between 12.18% and 17.71%. Repeat. We are 95% confident that beta 1 is between this and this. What is beta 1? Average change in purity due to 1% increase or decrease in hydrocarbon level. So we are 95% confident that the change in purity due to percent increase or decrease in hydrocarbon level is between 12 and 17%. Clear? Clear. Let's technical question here. If in exam I give you this confidence interval and I ask you to test whether beta 1 is 10 or not. H0, beta 1 is 10, H1, beta 1 is not 10. Can you test it? Using alpha equals 0.05. What are the three approaches of testing hypothesis? Critical value approach, p-value approach, confidence interval approach. Which one will you apply here? Confidence interval approach. According to the confidence interval approach, how do you make decision? If H0 belongs to the interval, you go with H0. Otherwise, you reject H0. Does H0 belong to the interval? It doesn't. So you will reject H0 in this case, and you will say that the average change in purity due to a unit change in hydrocarbon level is not 10. It's significantly different from 10. But what if the question was to test it at 10% level? Then you cannot answer. The level of confidence for the confidence interval and hypothesis test, it has to match. If it doesn't match, you cannot answer. You cannot answer a 10% based on 5% confidence interval, okay? So they have to match. Remember that. It's not a valid question. The next question says construct a 95% confidence interval for beta naught. And that should be beta naught hat plus minus T alpha by 2 multiplied by, again, this part is the standard error. You have already found this one. So this is MSE 1 over N plus X bar square over SXX. You have already found whole of this in question 4, I think. This is standard error of beta naught hat. You found it here, 1.5937. Can you see it? Can you see it? You found it already. So you will take beta naught hat, which is 74.2839. 74.2839 plus minus 2.101 multiplied by the standard error that you already found, 1.5937. So this one will give you a confidence interval between 70.9355 to 77.6323. Again, from here, what if I ask you to test the hypothesis that the intercept is 75? Yes, it is in the neighborhood of 75. You cannot reject the hypothesis that beta naught is 75 because 75 belongs to the interval at 5% level of significance. Good technical question. Read the question. This one. Let me highlight what is required. Can someone tell me what is the yellow highlighted thing? Beta 1. So you are supposed to test what? Again, chapter 9. How do we set up the hypothesis? We read the statement and write it as notation. What is the statement in terms of notation? Then we write the opposite. What is the opposite? Which one contains equal sign? Clear? Now to test this hypothesis, again, you will go to the formula sheet, and the formula sheet will give you this t statistic. It will give you beta 1 hat minus beta 1 naught over the standard error, which is MSE, over SXX. Again, this part is the standard error of beta 1 hat you have already found. Okay, you will plug everything inside and you will get, what is beta 1 hat? We got it 14.97. What was it? 14.947. 14.947 minus, what is beta 1 naught? The value of beta 1 that you want to test. What is the value of beta 1 that you want to test? 18. Divided by the standard error of beta 1 hat is 1.3169. 1.3169. So this t value comes out to be minus 2.3183. Minus 2.3183. From here, you have two options, either to go to the rejection region approach or you go to the p-value approach. Which one is easier? Critical value approach is easier. If the question does not bound you to use p-value approach, it is always easy to use the critical value approach. Okay, so using the critical, yes, the question might ask you to find the p-value and give the p-value. So if the question is not having a binding, you better use the critical value. So according to the critical value approach, you reject H naught. It's a two-sided hypothesis, right? If the absolute value of T naught is more than T alpha by 2 with 18 degrees of freedom. And this guy again is 2.101. Is the absolute value of this 2.3183, is it more than 2.101? Yes. So you will say as absolute of minus 2.3183 is more than 2.101, so we reject H naught. What do you conclude? What do you conclude? That the average change in oxygen purity associated with 1% change in hydrocarbon level is different from 18. Significantly different from 18. Clear? Is not 18. Yes. Significantly different from 18. It's not 18. If you fail to reject H naught, then you will say it is not significantly different. It means in the neighborhood of 18. When you reject H naught, that means it's significantly different. Any question? Yes. It was 5%. No. Which 5%? No. This is not alpha. This is average change in Y due to 1 unit change in X. Beta 1. This is whole beta 1. They did not mention alpha. You assume alpha 5% yourself. In the question, nowhere they mention alpha. This is the average change in Y. It's a pure luck that the variables are in terms of percentage. So it looks like this is alpha. It's not alpha. It's the average change in Y due to 1 unit. Percent is unit of hydrocarbon level here. It's not that alpha percent. We don't go into that one. It does make sense. It can become a question, but usually you don't expect something like that, that we give you a change of unit in terms of beta 1. Technical question. Read the question, set up the hypothesis. Again, the solution is easy, but setting up the hypothesis is tough. You have to test the hypothesis that the regression line passes through the origin. which means the intercept is 0, right? So the statement says that beta naught is 0, or sorry, 0. This is the question. What is the opposite? Which one contains equal? That's it. You will go to the formula sheet. You will get this one, beta naught hat minus beta naught naught over standard error. Plug it in. This was 74 point something minus 0 divided by, we already got this 1.5 something. This whole thing is actually the standard error of beta naught hat. As a result, the t value comes out to be 46 point something. 46.611. Again, you have the option to go either to the critical value approach or p-value approach. We already saw the critical value was 2.101. Is this bigger than 2.101? So we reject H naught. What do we conclude? The regression line does not pass through the origin. Any question? Reject H naught. That means intercept is not 0. That means the regression line does not pass through the origin. Part 10. What is the question? Test the significance of regression. What was the test we used for significance of whole regression? Testing for the significance of regression, if the regression is significant or not. If the regression is significant or not. What was the test we developed for testing the significance of whole regression? Let me remind you. We had yi equals beta naught plus beta 1 xi plus epsilon I. You remember? We said the total variation in y is equal to the variation because of regression plus variation not captured by regression. You remember? From here, we said if SSR is close to 0, the regression is bad, insignificant. If SSR is big, the regression is good. If your regression is explaining more, regression is significant. If your regression is explaining less, it is insignificant. But it was difficult to judge if it is close to 0 or close to SST. So we defined a statistic, which is SSR divided by 1 over SSE divided by n minus k minus 1. And we called it F. You remember that? And we said that if this F is close to 0, the regression is insignificant. Why? When will this F be 0? When the numerator is 0. When will the numerator be 0? When SSR is 0. And when SSR is 0, that means your regression explained nothing. Everything went to the error. But we said when this F goes to infinity, that means a big value. That means what? Regression is significant. Good regression. When will this be big? When the error is small and the numerator is large. When the numerator is large, that means SSR is large. Well, that means the explained variation is bigger, unexplained is smaller. That will push F towards infinity. Between 0 and infinity, you said there is a value above which we will make decision. This is 0, this is infinity. Here you will say regression is insignificant. Here you will say regression is significant. The cutoff point is what we call the critical value. Okay. The cutoff point is what we call the critical value, which will come from where? F table. So let us go now and see what is required here. Again, test that the significance of regression. For the significance of regression, your hypothesis is that all the slopes are 0. Against H1, that at least one slope is not 0. How many slopes do you have in the regression? There is just one for now. In chapter 12, there will be more slopes because there will be more features. There will be beta 1, there will be beta 2, there will be beta 3, and so on. You get the point? The topic actually belongs to chapter 12, but its special case is in chapter 11, where you have only one feature. If you have only one feature, you will have only one beta. So here you are testing that beta, all the slopes are 0. Let me write all the slopes are 0. But all slopes are just one slope, which is beta 1 in chapter 11. But in chapter 12, all slopes will be all slopes, right? So for this one, we have in the formula sheet F statistic, which is SSR over the number of features. Let me write again the general version, divided by SSE over n minus number of features minus 1. So we already found SSR for this example. What is SSR? There was one slide, I think we found SSR. Did we? Here. What was SSR? 152.1216. 152.1216 divided by number of features 1 divided by SSE. We found SSE in the same slide. 21.2553, 21.2553, 21.2553 divided by, what is the sample size? 20. How many features? 1 minus 1 from the formula. You plug everything in, you get the value of F to be 128.8238. Now, F table is an extended version of T table. In Z table, how many degrees of freedom did you have? No degree of freedom. Z table only depends upon alpha. No degree of freedom. When you extend it from Z to T, along with alpha, you saw a degree of freedom. When you extend from T to F, there will be 2 degrees of freedom. One of them is called the numerator degree of freedom, and the formula for numerator degree of freedom is here. This is V1. Numerator degree of freedom, and this is denominator degree of freedom, V2. So to go to the table, you need to find V1 and V2. What is V1 in this question? 1. What is V2 in this question? 18. So to go to the F table, you need V1, you need V2. Now go to the F table. Is alpha given to us in the question? So you will go to the F table where alpha is 0.05. For each value of alpha, there is a different F table. So let me show you now the F tables. Here are the F tables. In the top left corner, value of alpha is mentioned. So the first F table is given for alpha equals 0.25. Is this what you want? No. The second F table is given for 10%. No. The third F table is given for 5%. This is what you want. Okay. Within this F table, look, the numerator degree of freedom is up there. And the denominator degree of freedom is on the left side. So your numerator degree of freedom for this question is 1. Denominator is 18, is it? And the corresponding value of F is 4.41, right? So you will take this value 4.41 and you will compare 128 with that 4.41. So here you will say that F 0.05, 118, this is 4.41. You will say as 128.8238 is more than 4.41, so we reject H naught. And rejecting H naught is good. Regression is significant because your H naught was all slopes are 0, which means regression is insignificant. Slope 0 means regression is insignificant. You want the slope to be either positive or negative. That means there is a linear relationship. If slope is there, relationship is there. If slope is 0, it's insignificant relationship. So rejecting H naught is a good thing in this case. So you reject H naught and you conclude that the regression is significant. Now it's a pure luck that for chapter 11, we have another way of testing this hypothesis. Do you know that? Because all slopes is only one slope, in chapter 11, we have only one slope. Can I write this one as H naught that beta 1 is equal to 0 against H1 that beta 1 is not equal to 0? Is it the same thing? Can I also test it with the t-test? Yes, so you will get the same decision from the t-test. So t-test becomes a special case of f-test only for chapter 11. They will give you the same decision. But in chapter 12, there will be completely different things. T-test will be testing the individual slopes. F-test will be testing all the slopes together. Okay, so for this case, you can test it using T also. And the slides will tell you that in this case, your T square will be equal to the value of F. So if you find the value of T, which will be the square root of this 128.82 something. It'll be B1 equals 0. It is B1 equals 0. I'm saying all slopes equal 0. All slopes, there is only one slope in the regression for chapter 11. Yes. Why did we choose 0? Why did we choose 0? Because if the slope is non-zero, that means that X is having an impact on Y. Look here. If the regression is insignificant, you will have a scatter plot like this. Now in this scatter plot, when X is going rightwards, where is Y going? Nowhere. So if you fit the line will be something like this with 0 slope. Okay, if you fit a line on this model, the line will be a horizontal line with 0 slope or close to 0, with a value of beta 1 close to 0. So if the value of beta 1 is close to 0, that indirectly means that there was no relationship and the regression was insignificant. Why 0 is specifically important? Because of this. If you have a relationship like this, the slope will be positive. Similarly, if you have a relationship like this, the slope will be positive. But what is the difference between the two of the ones that you see on screen? The second one is more significant than the first one. So here the p-value will be even smaller. There the p-value will be small, but not as small as the one for the lower one. The lower one, p-value will be even smaller, or f will be even close to infinity, more close to infinity. Choose the slope to be 0.000. Will we reach the same? Yeah, 0.000 is the same thing. Yes, not a big difference. Yes. Yes. Sorry. Any question? Now, what if in this question they put a binding that you have to solve this question using p-value approach? If they ask you to use this question using p-value approach, which is question 11, again, you are asked to test the significance of the regression, but this time using p-value approach. The p-value expression is the probability in F distribution with 1 and 18 area above the calculated value, which was 128.8238. In F distribution, you have to find the area above this one. Now, this is a very, very tough question. Very, very tough question to get this area. Now, you must see in F distribution some of the critical values, and from there you have to guess this value. How to guess this value? Let me take you to the F table, and I will extract some values from the F table, and I will show you the trend, and from that trend, I will show you how to guess this value. Again, 128 point something, you will never find exact value. Like the T table, you will never find the exact value. So the P value will always be in terms of interval. How to get this interval? Let me show you. Go to the F table. And see the first one when alpha is 0.25 and get the critical value. What is the critical value? 1.41, right? Write the meaning of this 1.41 in your answer sheet. What does this 1.41 means? This means that probability that F118 more than 1.41 is 0.25. Write the meaning of this one. Then again, go back to the table and write the meaning of the next one. What is the meaning of next one? This is the table for 10%. Again, the critical value is what? 3.01. So write the meaning of this one. What does this mean? That probability in F distribution with 1 and 18 area above 3 point, what was it? 0.1 is 10%. Okay, one more. The next one, 4.41. I think 3 are enough for you to see the trend. Probability that F118 more than 4.41 is 0.05. Now look at the 3 of them and look at, let me continue. Let me continue. Last one. What is the value? 10.22. And what was the value of, what was the area above 10.22? 0.0020. So probability F probability of F118 more than 10 point, what was it, 10.22 is 0.005. Now look at these 4 values and try to see what do you require. When the probability is going down, what is happening to the value? Is going up, right? Now, where is 128.8238? Is it in between these values or even below the last available value? It is even below the last available value, right? So the area above that will be what? Less than 0.005 or more than 0.005? So your p-value is even less than 0.005. For this p-value, will you reject H0 or fail to reject H0? Usually the alpha is 5%, right? So against this p-value, you will reject H0. So for getting the p-value, you have to see the trend from the F table and see sometimes the value is in between the two, sometimes the value is on one extreme, sometimes the value is on the other extreme. So for this example, if the F value was 0.31, what would be the P value? If you get a question in exam where F value is 0.31, what would be the P value? 0.31. If the question gives you F to be 0.31. So the probability of F greater than 0.31 will be what? Greater than. So in that case, you will fail to reject H naught, right? What if there is a question which gives you probability of F greater than 2.79? Now 2.79 is between 0.1 and 0.25. So this is how you will get the P value from the F table. Most of the times it is close to 0. Most of the times F value is large, regression is significant, it is close to 0. Most of the time. Again, if it is an interval, you write as an interval. Then usually alpha is 5%. So the interval, the whole interval will be either on the left side of 5% or right side of the 5%. It's either fail to or reject. If the whole interval is on the less than side, then you reject. Now we get to the uses of regression. The first use of regression. No, not yet. What is the hypothesis here? No linear association, correlation is 0. Against? Which one contains equal? Again, for this hypothesis, you have a T value in the formula sheet given to you. In the formula sheet, it gives you R over 1 minus R square over N minus 2 square root. The formula sheet gives you. You already found the sample correlation. It was 0.9367. You remember? 0.9367 over 1 minus 0.9367 square over 18 whole square root. And this one comes out to be, basically this whole chapter is an application of chapter 9, 11.35. This one is 11.35. From here you have again two options, either to use the critical value approach or p-value approach. If you use the critical value approach, the critical value is 2.101. Is this more than 2.101? Yes or no? So we reject H naught. And we conclude what? There is linear association. Yes. Read number 13. Very important question. Read number 13. No, but similar. It's related. Same slide. Percentage of variation in Y that is explained by the regression. We defined a measure for that in one of the slides. Read the highlighted part. Percentage of variation in Y that is explained by the regression is measured by R square. SSR divided by SST. So this is what you are supposed to find. Luckily, it is equal to the sample correlation square. So if you already have sample correlation, just square it. You will get R square. Or you can find it using the formula R square equals SSR divided by SST. SSR, SST, I think we already found all of them. And they are 152.1216 divided by 173.3769, and it comes out to be 0.8774. which is actually the square of this number, 0.9367, exactly the square of this number. So what will you say interpretation? 87.7% of the variation in oxygen purity is explained by hydrocarbon level. The remaining 13% goes to the error. Clear? What if the question was, what percent of the variation in oxygen purity is not explained by hydrocarbon level? 1 minus this thing, 12 point something. Okay. Next question. Estimate the mean of y when x is 1.1. Mean of y when x is 1.1. Estimate that. What is that? We said it's simply beta naught hat plus beta 1 hat x naught. Fitted value, plug in 1.1 in the regression and you will get it. Next question. Predict the single value of y when x is x naught. Y naught when x is 1.1. We said this is the same, beta naught hat plus beta 1 hat x naught. We said both of them are the same. Point estimates are same, which gives me the value 90.7256. 90.7256. 90.7256. You remember last class I asked you, what if I ask you to guess the average of the whole section? 72. The score of a single student? 72. Point estimates are same. But the score of a single student fluctuates more. The average of a section fluctuates less. So the interval estimate for this one was wider and the interval estimate for the first one was narrower. You remember? Now go to the last question. Find a 95% confidence interval for mean of y when x is 1.1. So the formula sheet gives you mu hat of y plus minus T alpha by 2 MSE 1 over n minus x naught over x bar whole square over sxx. What is this? What is T? MSE, we already found that. What is 1 over n? 20 minus, what is x naught? Very important. What is x naught? The value of x at which you are doing the prediction. What is the value of x at which you are doing the prediction? 1.1 minus the mean of x. I think it was 1.196. I think, I'm not sure about this. Whole square over sxx. You already found. So solve it. Next question. See the relationship between these two questions. What does the last question say? Find a 95% prediction interval. Prediction interval is for mean value or single value? Single value. So the prediction interval will be the same formula, but 1 plus. So that will be y naught hat plus minus T alpha by 2 MSE 1 plus 1 over n plus x naught minus x bar whole square over xxx. So you will plug in the values. Let me give you the final answer and the interpretations of the two. The final answer for the first one is between 90.1501 all the way up to 91.3011. You see a very narrow interval. And for the single value, it gives me 88.371 all the way up to 93.0802. What will you say about the first one? What will you say about the second one? For the second one, you will say that for a sample where the hydrocarbon level is 1.1%, we are 95% confident that the purity of that sample will be between 88 and 93. The oxygen purity of that one sample, one observation will be between this and this. For that one, you will say for all the samples where the hydrocarbon level is 1.1, we are 95% confident that their average oxygen purity is between 90 and 91. So we wind up the class here. We are done with the chapter. In this chapter, we talked about the simple linear regression model. We found their estimates to be beta 1 hat, beta naught hat. We talked about the confidence intervals. We talked about the hypothesis test, including T and F tests, and they were used to assess whether the regression is significant or not. We talked about the proportion of variation in Y, which is explained by the regression using R square. We said that luckily it is equivalent to the correlation square. We talked about the prediction. In terms of prediction, we said two cases. One where we're interested in single value, one we're interested in average value. So number one is estimate the mean of Y when X is X naught. Number two is the predict the value of Y when X is X naught. The point estimates for the two of them are same, but the interval estimates for two of them are not the same. I was planning to cover these questions today, but I don't know if I will have time. Next class, I will probably start chapter 12. If at the end of chapter 12 I have time, I will come back to these questions of 241. Okay.